Yes, sir. Uh, Good afternoon, everyone. Am I audible to the last bench? Yeah. How many students are new? You're attending this school, attending this class for the first time? Okay, one, two, three, three of you. Okay, okay. I hope everyone is in the class. Yeah. Okay. We'll get started. Let me. Okay. Yeah. Yeah. All right. So students will be talking about relations and functions, basic mathematics. These are a couple of classes or maybe three more classes will be done with basics of mathematics. These are techniques or tools that we require in physics, like calculus. From chapter one, you would be using differentiation, integration, and all that, right? Vectors. These are certain things we need to revise. Yeah. Let's start with calculus. Anyone knows the story of development of calculus? How did it come into being? Who worked on it? Anyone? Newton, Bernoulli, and Gottfried Wilhelm Leibniz. Yes. So Newton and Leibniz both worked kind of independently to develop this, and there was a fight between them as who is going to take the credit of coming up with this. So anyway, there's no settlement on that. Still, people fight over that, but it's okay. We have the tool and we are free to use it. Newton developed calculus because he wanted to understand laws of motion better. So it was a problem in physics which propelled him to kind of come up with mathematical tools. And calculus is it's a proper chapter in mathematics. And what was the inspiration of that? He wanted to understand the physical world better, right? So we are starting on this journey where we talk about the basics of um, oh, can you come and help me, please? Okay, okay, thank you. So yeah, we'll be talking about relations and functions and graphs of functions if time permits. Relations. How many of you are completely unaware of what we are going to talk about? Like completely unaware, because there are some students that have bio as a subject and no idea, no clue what relations. Okay, okay, fine. What does the word mean? You understand the word, you know what it means. Here, the same meaning is there, but it's the relation between variables. Yeah. In order to relate or in order to talk about relation, you need two quantities. Like one is related to the other. Yeah. And those quantities are going to be variables here. When we talk about variables in physics, what comes to the mind? What do you think of? Variables, general variables. Time is a variable, yes. What else? Distance is a variable, yes. What else? Speed, velocity, acceleration, fine. What else? Let's move out from kinematics and think of force is a variable, yes. Field, electric field, magnetic field, gravitational field, all fields are variables. So you see one thing. that all these are physical quantities, right? All these are physical quantities, all these variables that you gave examples of, right? So in physics, when we talk about relations, we'll talk about relations between variables. And variables here are going to be, because we are considering things that are relevant to physics. So we'll be talking about where variables are physical quantities. Okay. Now, physical quantities, I hope everyone understands what these are as compared to abstract quantities, let's say. Yeah. Can someone define what is the difference between, or tell me what is the difference between physical quantity and an abstract quantity? Maybe give an example or something to first raise your hand and then I'll ask. Okay. Yes. Okay. And what are abstract quantities? Cannot be measured. Okay, good. Sit down. Someone else, can you give me an example of a quantity that cannot be measured? Something that cannot be measured. Because everyone knows things that can be measured. Soul. Oh, okay. Yeah. Oh, deeper. Yes. Good. Thank you. See, feelings. These are feelings. I mean, you cannot measure it. You cannot put a number to it, right? You know, you let's say someone asks you, how much do you love your parents? Okay, can't put a number to it. No, love 300 or 400. You can't do that. No. So that's what those quantities we cannot measure. Those are abstract quantities. In physics, we do not deal with such quantities. We'll only deal with physical quantities. So when we're talking about relations, we'll talk about relation between variables. One example, like a very simple equation, F equal to ma. Is this a relation? It relates three variables, right? So yeah, perfect. This is the relation. Okay. So any formula in physics that you see, it's all variables. I mean, it's all relation between variables. Okay. In fact, all the formulae in physics that you see, these are some special type of relation. There are some well-behaved relations, and then there are some non-well-behaved relations. Okay. Well-behaved relation is only what we deal in physics. Those well-behaved relations are called, any idea? Functions. Those well-behaved relations are called functions. So in physics, we'll be mostly dealing with functions. But since we're tackling relations, we should understand it in general, what it means, and then we'll move to understanding a special type of relation, which is a function. Okay. So what is a relation? I've put a data for you where temperature is measured with respect to time. So at different time intervals in a class, for example, the room temperature of this class, at time 9 a.m. or 9 hours, 12 hours, that is midday, noon, that's 15 hours, that is 3 p.m. and 6 p.m. We've calculated the room temperature, okay? That's a data. One variable, second variable. This is a relation between temperature and time. This is time, this is temperature. Any data, any such data do you see, that's a relation, okay? Whether it is well behaved or not, we'll talk about that later. So in physics, physically, a relation will basically be a record of how one thing depends on the other. Here, how temperature depends on time or how time depends on temperature? What is this a relation of? How is temperature depending on time or how is time depending on temperature? Temperature depending on time. Why did you choose specifically that? Because had I written temperature this side and time that side, you would have said otherwise? No, right? No. Why you chose time? You're saying that temperature depends on time. Yeah? What is so special about time? Or why not like time depends on temperature? What made you think that temperature depends on time and not time depends on temperature? Because if I just represent this by x and y, saying that x depends on y and y depends on x, saying that one is correct, the other is wrong, does not make sense to me. So my question is, why did you choose time to be that special variable? Time always increases. What if I have a controlled experiment where I ensure that temperature always increases? In that case, you will say that time depends on temperature. Yes, yes. Yes. Okay. So there are certain physical laws which gives you a hint which one is supposed to be an independent variable and which one is supposed to be a dependent variable. So independent and dependent variable are the key for us. Whenever we do certain experiments, sometimes we are free to choose what we want independent variables to be, and sometimes it'll be automatic. If you're comparing something with time, of course, change recording how temperature changes with time, that's much more convenient. Yeah. Okay. So in physics, it's basically a record of how one thing depends on the other, or you could say linked to the other. Example: time and temperature, force and acceleration. Now, if I write force equals mass into acceleration, what would you say? Does force depend on acceleration or acceleration depends on force? How many say force depends on acceleration? Raise your hand. Okay, good. How many say acceleration depends on force? Raise your hand. Okay, both of you are correct. I mean, both the answers are correct. Yeah. So how do we decide which one is an independent variable and which one is a dependent variable? Yeah, that depends on the experiment, the kind of experiment we are designing. For example, if I'm designing an experiment where there's a block of known mass and that mass is fixed, I am applying different values of force. So F1 or force here, acceleration here. So I'm changing force. So first I'm applying 10 Newton, then 15 Newton, then 20 Newton, then 25 Newton. Okay. And based on, for every experiment, I'm recording what is the acceleration. So I have a device which captures what is the acceleration of the object. Okay. So if I've applied 10 Newton of force, the acceleration comes out to be maybe 2 meters per second square. 20 newtons of force, it'll be double, 4 meter per second square, and so on. Okay. So for this, it'll be 3 meters per second square, and so on. Okay. So now what's happening? Force, I have control over. I am changing this. Okay. So I'm free to choose. For my experiment, force is what I am free to choose. The experimenter is free to choose. And what we are recording is the acceleration. So in this case, now tell me what is the independent variable and what's the dependent variable? Force is independent. Force is independent because the user is free to change that, and based on that, we are recording acceleration. Okay. Now, someone can design another experiment where by some mechanism, you're changing the acceleration. Okay. So you have control over what acceleration shall be given to an object. Okay. By some device, some mechanism. So then you're changing acceleration. Okay, acceleration is 1 meter per second. Then I'm calculating, okay, what is the impact it makes? Okay, so just throw something with some acceleration. What's the impact it's making? What is the force exerted by it on a wall? You throw a ball with acceleration 5 meter per second. What is the impact on the wall? Throw it with 10 meter per second. What is the impact with the wall, and so on? So in that case, what becomes the independent variable? What becomes the acceleration becomes the independent variable, right? And force becomes the dependent variable. Okay. So I hope in relation to physics, it's important to know what is what is independent and dependent variable, because we'll be setting up experiments based on that. So what quantities do I have to find out and what do I have control over? That decision is important if you want to find out something. Anyway, mathematically though, the definition is more generic. In this case, you see, it's a collection of ordered pairs. Now, I know many of you would not be aware of this term, ordered pairs. Looks like a fancy term, but it's very, very simple. In this case, let me write this data in like this, okay? 9, 24, 12, 31.5, and so on. Am I writing it in the form of A comma B? Yeah. That is what we call as an ordered pair. Ordered pair means, why ordered? Because A values will always be written first. That's why it's ordered. You cannot write this as 33 comma 15. That would be wrong. Okay, that's not an ordered pair. Okay. So pair because two. Ordered pair because you have to ensure A is always in the same column and B is always in the same column. So that's why it's called an ordered pair. So mathematically, what is a relation? It's basically a set of ordered pairs. Any data with two columns like this can be considered a relation. Here also, if I ask you to write the ordered pairs, how would you write? Would you write 2 comma 10 or 10 comma 2? 10 comma 2, 2 comma 10. What's the problem with that? Yeah, yes. Now, if you know that, then fine, but I haven't told you that yet, right? So we were coming to that. Okay, good that you know. So, okay, by convention, we write the independent variables in the first column and dependent variables in the second column. So, independent variables would be written here. So, ordered pairs for this would be 10 comma 2, 15 comma 3, 20 comma 4, 25 comma something, okay, 5 and so on. Now, mathematically, a relation is not just one ordered pair, it's a collection of ordered pairs. So here you have 4 items, 4 ordered pairs. A collection of 4 ordered pairs is called a relation. Okay. So mathematically, if I have to write relation, which relation do you want to write? Force acceleration or time temperature? Tell me. Force acceleration. All right. So relation, it's a collection of ordered pairs. Collection, by the way, in mathematics is a set. Have you heard about that? Set theory, yeah. Let's write in roster form. So where within curly braces, you just list the items. For example, if I ask you, what is give me a set of natural numbers smaller than 5. So within curly braces, you write 1, comma 2, comma 3, comma 4. That is it. Yeah. So that's a set. Anyway, so this relation is also a set, but a set of ordered pairs, not singular items. Okay, it's a set of ordered pairs. So R is equal to something, comma, something like some ordered pair, comma, some other ordered pair. And we have 4 items, so we can close the bracket now. Okay. Let's list those items now. So force and acceleration, if you want to write down, you would write 10, comma 2, 15, 3, 20, comma 4, and 25, comma 5. So that is a set. It's a collection of ordered pairs. It's a relation. Okay. This format of excuse me writing is called the roster form. Roster, I mean, list of items is called a roster. That's why roster form. And then another form is set builder form. But you learn that in mathematics. Okay. It's not relevant here, so I'm not going to delve into that. Okay. Okay, independent and dependent variables we have seen already. But let's talk about, since we're talking about sets, and here we had force equal to mass into acceleration, and we had a relation which was given as a collection of some ordered pairs. This is a relation. Now, the first item of these relations was which physical quantity, was which variable? The first item, independent variable. And what was that specifically for our example? Force. Yeah. So force, I mean, from here you could say we have 2 sets. One is the set of forces, different values of forces, and another is the set of different values of accelerations. Okay. So sets, I'm going to write those sets individually. Force. What were the values if anyone remembers? 10, 15, okay, 20 and 25. All right, this was our set. This is one of the sets. Second set is acceleration. It was 2, 3, 4, and 5. So now we have two sets, okay? And you see that the length of these two sets is the same, or the cardinal number of these two sets are the same, or the number of items in the two sets are the same. Yeah, that's not always necessary. You can have two sets with different number of items in them, and still there can be a relation between them. For example, your roll numbers versus the marks that you're getting in an exam. Okay, it's possible, no, that two people get the same marks. It's possible, right? Yeah. So that the second set may not have as many items as the first set. Like roll numbers will have all like 52 of you, okay, 52 items in it. But the marks item may not have 52. It can have 50 items in it. Yeah. We always put unique items. We cannot put two times. Okay. So set now these are individual sets. And a relation between these is represented by different ways. One is using this, another is by using a Venn diagram. And this is really easy to understand because we understand pictures better than statements. Okay, so Venn diagram, it wouldn't look much of a diagram by the way, but so one set, the independent variable set would be drawn first. The second set, acceleration, would be drawn next. Within these two sets, you are going to have the items. You list all the items of 4, so 10, 15, and there's no need to put it in order. You can jumble them up also, it doesn't matter. So I'll put 25 and 20 here. Yeah, that is your first set. And the second set, similarly, we'll write 2, 3, 4, 5. So 4 items here, 4 items here. And there is a relation between the two. What is the relation? That relation would be drawn or would be shown using a ray. Yeah, ray going from the first set to the second set. So if I want to relate one item of set A to one item of set B based on the relation that I already found out earlier, 10 to 15, 3, based on this relation, now we'll draw this relation pictorially. So 10 maps to which number here? 2. So from 10, you draw a ray like that, and that 10 is mapping to 2. 15 is mapping to 3. 25 is mapping to 5. Goes like that. 20 is mapping like that. Okay. So that is a relation. Okay. And this diagram, this type of diagram is called a Venn diagram. Okay. Relations, if we have to write out, this relation can be written as relation is F equal to MA. Now, since F is the independent variable, while writing it as formula, independent variables should be kept on the right side or left side. What do you think? While writing it as an equation, independent variables are usually kept on the left or right. Independent variables are kept. Are you sure? In the equation, not in the Venn diagram. In an equation, have you seen this? Y equals f of x. Yeah. So that's independent variable is plugged in here. Okay. But it's not that important a convention. F of x equal to y is also as correct as y equal to f of x. Okay. But anyway, so this relation, if I have to write out the relation between f and a, I would write a equals f by m. Yeah. Y equals, this is what we write as y equals f of x, where actually I won't be using functions yet. Let me just write relation. Okay, y is some kind of relation of x. Functions we haven't talked about. Okay, so y equal to some kind of relation where x is the independent variable and y is your dependent variable. Because for our experiment, this this quantity depends on force, and that is why we have done this. So y equal to a relation of x, one to one mapping, one object having one image. It's a function. Such relations are called functions. One item when it has only one image, one and only one image, then it's a function. Okay, so a special type, and that is what we call as a well-behaved relation. That's a function. We'll get to that. Okay, so eventually you will see me writing things like y equal to f of x. Okay, so I hope everyone understands what this means now. It's basically a relation between an independent variable and a dependent variable. Clear? All right. Venn diagrams is clear, set is clear. Okay. Now in set theory, you're going to learn about, uh, f cross a, f minus a minus f, and all those things. You'll learn that in maths. Okay. It's not relevant here. Right. In this case, can you identify which one is the independent variable here? Time is the independent variable. Position we are measuring. Position depends on time. So this is your dependent variable. In that case, for this equation, tell me what is the independent variable. What's the independent variable here? Force. Okay. So here acceleration again will become dependent. Force would be independent. Had I written the formula F equal to ma, Newton's second law, then you would say, all right, A is the independent variable here. Okay, as per convention. Okay, but actually what it depends on is the experimental design, experimental setup. How you represent that mathematically, we're just following convention, so that just by looking at the equation we can figure out, okay, what was kept as the independent variable. Okay, so that's why we are following a sequence, a convention which is followed everywhere around the world. Okay, so yeah, independent variables are the variables that you are free to choose. Dependent variables are the variables that depend on the independent variable, or values that depend on the independent variable. Although dependence is mutual, but for experiments, we are tracking dependence on one particular quantity, dependence on the independent variable, dependence of the desired physical quantity onto an independent quantity. Okay. And we'll draw graphs also. We'll have several functions and we'll see how the graphs look like. And in graphs, the graphing convention is, when you are drawing a graph, ensure that on the x-axis, you're putting your independent variable, and on the y-axis, you're putting your dependent variable. That's the graphing convention. Okay. All right. I mean, if someone flips it just for the sake of it, the physics isn't wrong. But we want to settle on a convention so that when your paper goes somewhere else, and for example, it goes to New Zealand, okay? Now, a person reading your paper should not get confused. You wouldn't want to keep your paper confusing, right? And that's why we were following some specific conventions. Okay. So, yeah, now let's come to the confusing part. Might confuse a few. Functions. By the way, domain, codomain, and range, it's defined for relations as well. Okay. For now, just pause on the functions part and let's see, I have a relation x and this quantity b. Set A denotes x, set B denotes the quantity 2x plus 1. Okay. We can call that y also, but it's already called b, so let it be b. Okay. Now, what is the independent variable? Can you identify from here? X. Yes, x would be the independent variable, right? This is not written x equal to 2x plus 1. Yeah, that is not that. Okay. In Venn diagram, whatever is the first set, that's your independent variable. So this here, this, I mean, this x is your independent variable. Independent variable. And this quantity is the dependent one. Now you are free to give it a name. Okay, you must be measuring some quantity. Okay, you can call it acceleration, you can call it whatever quantity that you are measuring. Okay, want to give it a name? Okay, that's a good name. That's the convention we use. Okay, so this is y, this is x. Now y equal to 2x plus 1 is your equation. Okay, if you have to write the equation for this or the relation for this, you are saying basically y, the dependent variable, is equal to, how does it depend on the independent variable? How does it depend on x? Can you tell me? How does it depend on x? Yeah, what's your name? Look it. Okay, what should I write here? Yes, 2x plus 1. 2x plus 1. Now, x is the independent variable, right? So, dependent variable on the left hand side equals how it depends on the independent variable. That's your function. And these kind of relations you are going to see every time. Have you seen this? Um, v equals u plus at. Anyone has seen this in physics? Yeah. Isn't this of this form? Yeah, where time is the independent variable. This is a constant, suppose. And you have this v is what you are finding out. So v depends on time, like that. So now if I ask you to draw the Venn diagram for this, would you be able to draw it? Draw it? Yeah. There will be a problem though. Here x values are discrete. But time value, is it discrete? Like time 1 second exists, time 2 seconds exists. Is there no time between 1 and 2 seconds? There is, right? So discretely you cannot put the values, right? Yes, we can record values at discrete time intervals, that is a different thing. But time in a sense, how can it vary? That decides what is the domain of the independent variable time. So time can take values. What kind of values can time take? Can time be negative? No. Can it be 0? Yes. If I'm starting the experiment, I can decide, okay, let me call this time interval as 0, t equal to 0. So time can be 0. Can it be positive? Can it be an irrational number? Yes. Yeah. So all real values, in fact, the positive real values, positive real numbers, those are the values that time can take. Okay. So that would be called the domain of time. Okay. So any function or any relation, so there is a domain of definition and then there is a codomain of definition. So domain and codomain depends on how is a function defined. Let's come back to our case. Here, someone defined two sets, set A and set B, and said there was a relation between those two sets. Let's write those sets. Set A, that contains 1, 2, 3, 4, these 4 items. Set B contains 1 to 10, okay? 1, 2, 3, 4, and so on till 10, okay? Now you see these two sets are not of the same length, not of the same size. We have discussed that, okay? That can happen, there's no problem at all. The domain means in the definition of set itself, we have ensured that, okay, X can take only these values. Yeah, because these are the only values available. So whatever values X can take as per the definition of the function or the relation, that is called the domain of definition. Clear? What is meant by domain? Yeah. Okay. So that's why 1, 2, 3, 4. If someone asks you to write the domain, you could say, all right, it's 1, 2, 3, 4. Okay, that's the domain of definition. Okay. Similarly, if someone asks you, what's the codomain? Codomain means it depends on the definition of the function, first thing. The function was defined and this was not given. Okay. Only the two sets were given to you. Second function was told, it was told that second function has these many items. That is the codomain of the function. All 10 items are the codomain of the function. Is domain and codomain clear? Domain, codomain both depends on how is the function defined or how is the relation defined. But how many actual values are we getting? That is a different story. That is something we call range. So here, if someone asks you the codomain, it's going to be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. All those 10 items are going to be the codomain. Okay. Range, however, the set of outputs actually attained. Where am I getting this output from? From the function. You input something into it, you get an output. So a function can be, I'll get back to this slide in a bit. We'll get to this question also. Okay, I don't have a slide on that. Hold on. So a function can be understood as a black box, okay? Function which takes in an input. What kind of input? An independent variable, and gives you an output. What kind of output? Whatever we are looking for. So something that takes in force and gives you acceleration is a function. Something that takes in something that takes in velocity and gives you kinetic energy is also a function, right? So kinetic energy equals half mv square. Now you substitute v here. This is kinetic energy function, gives you the kinetic energy. Okay. Yeah. So coming back to this, domain codomain was solely based on the definition of function. Okay, these are the ranges that X can take, and these are the ranges that Y can take. But what are the actual values Y is taking? That constitutes range. Are we clear? The actual values. How do I decide the actual values? All right, this is our relation. This is what is going to decide the actual value. When I put X equal to 1, what do I get? When X is 1, Y is how much? Tell me. Put it here and tell me. Yeah, 3. Okay. When X is 2, 3, 4, we'll do that one by one. But okay, when X is, let's say, 4, what value of Y am I getting? I'm getting 9. When X is 2, Y is 5. When X is 3, Y is 7. All right. Y is 7. So now, any other values would you get? If there are 4 values of X and the function is a linear function, you will get one image of each. Okay. It's not possible that you'll get 2 values here. So 3, 9, 5, 7, this is the range of the function. Confusing? Yeah, it's okay. It's okay. First time, I mean, this is a chapter which is, taught for a month and we're doing it in a day. So it will be daunting. Which part is confusing? Tell me. Range, the difference between range and codomain, is that confusing? Yeah, okay, I'll explain that again. Is that okay? Same? Okay, okay. Okay, let's understand it by this example. We have So range versus codomain. Range and codomain. You have two buckets, two sets, all right? In one, in this bucket, you have four balls of different colors. You have a red one, you have a yellow one, you have a blue one, and what else? Okay, you can have a green as well. These are the four balls in this. Here, you have many red balls, but of different shapes. Not balls, then items. Okay, so you have okay, yellow, fine, yellow also. Okay, so you have some items of this shape, some items of this shape, some items of this shape, and so on. Similarly, you have for red, blue, and green also. You can. I'm not going to draw all those. Okay, so you can understand. Now, the quest is, or the game is, you're blindfolded. You have to pick one ball from here. Okay, you pick one ball and see its color. Then from the second set, you pick all the balls that are of that color. Okay, simple enough relation, right? Simple enough function. Now, in order to understand the difference between domain, the range and codomain, let's have some pink balls also inside. So we have like this, and different shapes. Okay, and let's have some. There are of course green ones. There are green ones, and there are red ones, and then there are some other colors. We'll pick orange also is there. Okay, codomain is going to be all these, whatever is there inside. But range, can you ever pick the orange balls? In any trial, would you be picking orange balls? No, because there's no orange ball here, right? So it won't allow you to pick orange balls. Would you be able to pick the pink balls? Right? So you see, range, the set of range is smaller than the set of codomains. Do we see that? Yeah. So that's why we say that range is a subset or a proper subset. Range codomain. I know this sign would be a little, it means it simply means that this is smaller set than this. That's all. Okay. Subset like um, okay. Let's say mango trees are a subset of trees. All kinds of trees, it has all different trees. Okay. Mango trees are just a subset of that. Similarly, range is going to be a subset of codomain. Codomains are these are bigger sets, and these are smaller sets. Smaller sets, but all these lie within this. Okay, any item from this will definitely be present here. But an item from here, I cannot claim that it must be the range also. That is making sense? Okay. Okay. Fine. So range and codomain is clear. Let's get back to that. Let's just write finally then what is the range. If someone asks you the range in this case, can you tell me what items would be in the range? Look at the diagram and tell me. 3, 5, 7, and 9. Yeah. Yes. 3, 5, 7, and 9. So range would be 3, 5, 7, 9. That is it. Okay. So I hope sets clear, not entirely, but whatever I think the simple way we did. Yeah. Fine. Range, codomain and domain. It's clear. See, you won't get confused with codomain and range, because when we talk about functions, we'll only be talking about domain and range. We'll forget about codomains. Okay. When we are talking about functions in physics, we'll be focused on the domain and the range. Okay, is that clear? Fine. Let's move on. Here's a question. This you can try now. This you can try. I'll read it out to you. Is it visible to you? Can you see what is written? Yeah. Okay, then try it out. See, those who know this properly, you'll have to bear with me, because there are some students who are, we have to take everyone along. This format is called the set builder notation. The thing I said you don't need to worry about. Okay. It's called the set builder form. Basically, it tells you, you can read it as there is a relation between A and B such that A plus B is always less than 10. That's how we read it. There's a relation between A and B such that A plus B is always less than 10. This is what we call as the set builder form. But you write everything in the roster form. So write A in the roster form. Give me all the elements. Okay. All positive even numbers less than 10. Is 0 an even number? Is 0 an even number? No? Yes? No? What is the definition of an even number? So divide 0 by 2. What are you getting? So is it 0? 0 by 2 is 0, right? Yeah. So it's an even number, right? Is it? Yes or no? Yes. Yes. By definition, it is. Is it a prime number? No. Is it a composite number? No. So prime and composite, no. But yeah, it is an even number. Yes. Anyway, so you could write 0. Oh, but it's specifically mentioned positive, no? So you can't write 0. We're not writing 0 because it's not a positive number. That's why. It is an even number, okay? So we'll write 2, 4, 6, 8, 10. Shall I write 10? No, because it's written less than. There's another expression which is less than equal to. If you had that, then we would write 10 also. Okay, so that's A. Similarly, B. All positive odd numbers less than 10. 1, 3, 5, 7, 9. Am I missing something? We're done. Okay. Now the relation is R equals this. So the relation R would be a set of ordered pairs. We have seen that. Yes or no? Now you have to fill in these items. Do that quickly based on that relation. A plus B is less than 10. Pick A from here. 2. Okay. I mean, there may not be just 4 elements there. So I'm just removing this. There can be many, many elements. So we'll see. If I choose 2, what are the possible values of B I can pick? 1 can I pick? Fine. Then 2 comma 3 is also fine. It's less than 10. 2 plus 3 is less than 10. What else? 2, 5, 2, 7, 2, 9 can I pick? No. Okay. All right. So 1 has been mapped. Let's pick the next one then. 4, 4, 1, 4, What else? 4, 3, 4 and 5. Okay. No more. Okay. Then we have 6, 6, 1, 6, 3. That is it, no? Okay. Comma, then 8, 8, 1. Anything else? No. Fine. So that's our complete relations, the set of all the possible values that follow this rule. Okay. Now, you tell me the domain, you tell me the range, tell me the codomain. Quick. Domain is this, no problem there. Okay. What is the range? 1, 3, 5, 7. Okay. I see. Yes. So range, I'll just write the range because that was the motive. So you understand range. 1, 3, 5, 7. And what is the codomain also? Tell me. Yes. Codomain is all this. Yeah. So now do you understand the difference between range and codomain? That's equal to 1, 3, 5, 7, 9. And this is, when we say range is a subset of codomain, do you understand that statement as well? Range is a subset. Or one can say codomain is a superset of range. Okay. These are some technical terms. Again, we won't be using these terms in physics very often. Let's move to what we'll be dealing with. Two sets, two variables, one relation. So there's one relation, and I'm going to talk about different types of relation that can exist in nature. The relation between momentum and kinetic energy. Pick one value of momentum, you'll get one value of kinetic energy. The relation is, anyone knows kinetic energy in terms of momentum? Yes. Okay, some formula. Okay, P square by 2m. Put one value of P. If you put P1, you'll get Ke1. Yeah. Put different value, you'll get different value of kinetic energy and so on. So one value of P1 maps with one value of kinetic energy, one maps with another, and so every unique item here has a distinct, only one image, and all those images are distinct. Such kind of relations are called one-to-one relations. One-to-one relations. Okay. One-to-one relation, or one could say one-to-one mapping. That's also fine in terms of how we use the terminology. That is fine. Now let's move to this one. It's a relation between a projectile being launched, different types of launches, and we are writing the range here. Is it possible to get the same range for two different types of angles of projection? Yes. All complementary angles, keeping everything same, something you project at 30 degrees and something you project at 60 degrees, they have the same range. We know that, right? So let's say u1 is the same. Here also I take the same value, but theta 1, this is 30 degrees, this is 60 degrees. Both are going to give you the same range, yes or no? Yeah? Okay. Now, such relations are called many-to-one relation. Many-to-one mapping or relation. Many items in the first set can map to a singular item, so we call it many-one relation. Okay. Let's move to a different type of relation. One to many. I mean, one to many. So let's take this, x square is equal to y square, or rather, this is also fine actually, but since we have need students, you can just take x equal to y square. That should also work. Okay, forget about this one for now. X equal to y square. So you can have two different values of y which would give you the same value of x. Yeah. Or for one single value of x, you can get two different values of y. Yes or no? One positive, one negative. You know that. Yeah. If I take x as 4, y would be plus 2 also is possible and minus 2 is also possible. So plus 2 here, minus 2 here. You see that? So now one object is having two images. So one many relation. One to many relation. Okay. This type of relation is not a function. The above two, they are functions. This one is not a function. This one also is not a function. Many to many is also not a function. Clear? Okay. I mean, in order to remember it, you can think like this. Okay. If one object should have only one image, if that rule is being followed, it's a function. Here also one object has one image. It doesn't have two images. This is, we can consider object. And I mean, in mathematics also we call this as objects and images. But yeah, objects, images. One object having one image only, that's a function. That's a good relation. It's a well-behaved relation. Here also, one object, does it have two images? Does it have two images? No, it doesn't have two images, right? So that's also a function, as long as that condition is satisfied. So, I mean, in order to remember that, think of like one object cannot have two different images, like shadow, Considering there is one source of light, one object will not form two different images. Yeah. So that is a good scenario. I mean, that is a realistic scenario. How is this possible? I mean, you can have one object stand behind the other object and the images can overlap, right? But yeah, one object is having only one image. As long as that is satisfied, we are good to go. Here, what is happening here is like one object is having two images. It's not a well-behaved function, not useful, not really useful for physics. Okay, so we are going to ignore these two types and we are going to stick to these two types only. Okay. Yeah.
So that kinetic energy and momentum relation should be a example of magnitude.
The kinetic, okay, good. Kinetic energy and momentum. Okay, so this is the magnitude of momentum. Momentum is a vector, yeah. P square, no? How can you square a vector?
So like if we put P equal to plus and minus, will we get the same? So if we take
Okay,
all-
but it's a magnitude of the momentum in this formula. Okay, momentum negative, not making sense here when you put it in this formula. Consider it like kinetic energy is half mv square. You would say the same thing, no? Yeah, because we can take positive and negative values. Yeah, but kinetic energy, can it be negative ever? No. So what we are dealing with is this speed actually. That v is not the velocity, it's the speed. Yeah, so mv square we take, no, that's the speed. Here also it's the magnitude of the momentum. P dot P, but that's not the formula. The formula is not P square cos theta. Kinetic energy, it's a scalar quantity, right? Yeah. P dot P, it'll, yeah, okay, you can take that. The angle between them would be 0. So yeah, not a problem.
So when you take a speed of V, both sides will give the same kinetic energy. So we should get a sorry. Like when an object is going towards left and object is going towards right with the same momentum,
Okay.
their kinetic energy must be the same. But
Kinetic energy is the same, but see, this relation, it's defined for, I mean, the P values are all going to be positives. Okay. I mean, see, because the negative sign is itself canceling out. Yeah. So it's just like you're looking at things going in that direction and then you're changing your perspective. How would that change the relation? Changing the perspective won't change the relation. Mathematically, yes. Yeah. But here the limit is put by physics. That in kinetic energy, it's not the velocity, it's the speed. Yeah, half mv square. Yes, you can represent it as v dot v, and you can say yes, a vector product of two. A scalar product gives you a scalar, but that's actually speed because v dot v is essentially the magnitude square. Cos theta is 0, right? So yeah, so there basically the domain of definition tells you that okay, we are restricting to the positive side only. That is why it becomes a one function in the domain of definition. Tan theta is not even a function. Yeah, but we restrict the domain so that we can call it a function. Only when you restrict the domain. Oh, so yeah, okay, it's a function. Tan inverse theta is not a function, right? So when you restrict the domain, then only you can call it a function. Okay. Anyway. All right, a few questions, very simple ones. Let's see if you can do this. I'm going to ask some of you. So, is the font visible? Can you read it? Okay. Okay, question number one. Let's ask, can you tell me what is the answer to the first question? What's your name? Navya. Okay. What's time is the independent variable? Yes, that's correct. All right. All right. This, let's ask you. Beside, yeah. What's your name? Oh, yeah. Yes, yes. Okay. What is the answer to this one? Second one. 1 1. Okay. Okay. Sit down. Any changes? Do you think it's 1 1? Many 1. Okay. Because different students can have the same marks, right? So many 1. And this one, y square equal to x. Oh, interesting question. Is y a function of x or x a function of y? What do you think? Okay. Yeah, x is a function of y. Yes. To how many of you is it clear that x is a function of y? And just raise your hand, show once. Okay, okay, good. Okay. If you're confused, draw the independent variable here, dependent variable here. So y square equal to x. For one value of x, I can get two values of y, right? Yeah. So let's say this is x, I'll get plus y minus y. Or let me write y1 and y2. y1 and y2. If x was your independent variable, is this a function or a relation? Is this a function? It's not a function, no? One to many, it's not a function. So x is, you said x is a function of y, is it? Oh yeah, so y is not a function of x. Independent variable, dependent variable. It's not a function. So we can say y is not a function of x. Yeah. But if I flip it around, I mean, so you have y1, y2, and here you have x. The mapping is still the same, is it not? Now tell me, is this a function? This is a function. So we can say x is a function of y. Following? Yeah. So yeah, that is correct. Okay. But always drawing Venn diagrams to understand things, it's going to be a lot more time taking. So we have a solution for you. It's called the vertical line test to figure out whether a function is well behaved or not, or a relation is well behaved or not. Take, for example, equation of a circle, x square plus y square equal to radius square, where this is the radius, and that's your origin, that's your y-axis, that's your x-axis. That's the relation between x and y. Irrespective of what you choose as the independent variable, this function, this relation, it's not a function. Why? In this case, since we have plotted x here, let's call this as the independent variable. Whenever you find that one object or one independent variable can give you two different values of dependent variable, is it a function? one independent variable, one object having two images, is it a function? Yes or no? A little louder. Yes or no? It's not a function. Okay. And let's see what is happening here. Let's pick one value of x. Let's say x is equal to 1 centimeters. At this value of x, what is the value of y? You can go here and one can say, okay, I've found one value of y. But you can go down as well. You found another value of y. Yes or no? So if you draw, in fact, on any function, like you have a function, you have a relation represented on the graph paper, draw a vertical line anywhere in the domain of the function. Like don't go beyond this, don't go beyond that, stick to the domain. If you draw a vertical line in the domain and you see that the line cuts the function, the actual function, this orange circle, at more than one location, it's not a function. If this vertical line cuts the graph at more than one point, it's not a function. Is that making sense? Because one object cannot have two images, right? Okay, I'll give you some more examples. You can tell me whether those are functions or not. Okay, we'll get to that. I'll just add a page, from here. So my drawing is really not that refined, okay? But yeah, as long as you understand the physics, I'm okay with it. Is this a function? Is this a function? Okay, this is not a function because if you draw a vertical line, you see it's crossing at three different points. Yeah, not a function. One object is having three different images. But here, uh, draw a vertical line and you can move it around also. Anywhere you draw this line, keep moving this, you'll see everywhere it's intersecting only at one point, okay? Nowhere you will find that it's intersecting at 2 points. So that's a function. This is a function. This is a relation, yes, but it's not a function, okay? So this is a function. And we just talked about what we know as the vertical line test. So in order to test a function, in order to test a relation, whether it is a function or not, draw a vertical line, a line parallel to the y-axis. If it cuts at only one point, then it's a function, otherwise not. So this one is. Ensure that you're always dealing with independent variable on the horizontal axis. Only then you apply this test. This is not a function. And what we've just learned about is the vertical line test to check whether something is a function or not. Okay. Yeah, I mean, we've already made this journey, but okay, let's do a quick revision. What kind of relations are functions? A function relates each element of a set with exactly one element, meaning exactly one image. One object has to have only one image. It cannot have two images, otherwise it's not a function. So that's the Venn diagram for independent variable, dependent variable. Okay. And we've already discussed that one-to-one and many-to-one mappings are functions. The other two types, that is one-to-many and many-to-many, are not functions. Okay. All right. Draw these graphs and then tell me which one is a function and which one is a relation. I mean, which one is just a relation, not a function. y square equals x. That means y can take both positive and negative values. Y can take both positive and negative values, but it's going to give you a unique value of x. So, I mean, we'll see how to draw graphs of these things also, okay? But that's what it's going to be. Yes or no? Yeah. And here, again, xy axis, you can, it's going to be this. Which one is a function? The second one is a function. Use the vertical line test. This is yx. This is a function. And this is not a function. Why are we so interested in functions?
Usually it is because, like, example of position and time, one object cannot be at two positions at the same given time.
Yes. Yeah.
One object cannot have two accelerations for a given force.
Yes, but while learning physics, okay. So that is telling you why one to many cannot be a function. Yeah, you're giving an example of that. I'm asking, why are we studying about functions at all? Like, it's a topic of mathematics. Why are we studying here? Yes, we can relate it to some scenarios when we try to distinguish between one, many, one functions. But why? Is there no broader use of functions in physics? Okay, so one answer can be yes, we have several formulae and where variables are related to each other, and you will find that almost all those variables, all those relations are going to be functions itself. So what? I mean, it's a function and I'm just calling it by a name, functions. Is there anything else we do with these relations?
The entirety of calculus.
And why do we need calculus? Yeah, go ahead.
The entirety of physics is based upon formulas, right?
Yeah,
Formulas
okay.
and calculus, and it is all based upon functions. That's why we like.
Okay, I mean, those are functions we have identified, Siddharth. We have identified. What do we do with those functions? We analyze those functions, right? We operate on those functions. We see how. So you'll see, okay, how does a graph look like? Okay, so first thing we'll do with functions is we'll plot the functions. Linear graph, a linear variation, quadratic graph, cubic graph, trigonometric graph, sine functions. In different chapters, you'll have different functions or different types of functions, different categories of functions. So functions are there, so it's important to know that. Not only that, we have to analyze the function. We have to see the rate of change of displacement. What is that? Velocity. Yeah. So if you have the plot of displacement versus time, from the plot you could find the rate of change. Okay. Work done. Force F dot ds, the integration of F dot ds. Okay. Work done is force into displacement. We know that, right? If let's say I've plotted force on the y-axis and displacement on the x-axis and a constant force was acting on an object, could I say length into breadth, area under that curve will give me the work done? Yeah. So if you have graphs, analyzing graphs, if you have graphs of functions, analyzing graphs of functions, playing around with graphs of functions gives you a lot more insight into what is going on, what is happening in reality. Yeah, what is happening physically. And that is why we need functions. Okay. We've already seen this, the vertical line test. This is a function, this is not a function. We've seen this as well. Oh yeah, okay. I mean, it has been answered, but you just go through this. Why do physical laws almost always have to be functions? Why cannot you have two different values for one quantity? Like someone is doing an experiment here and finding out that if I drop a ball from the top of a tower of 100 meters height, the velocity at the bottom is so and so. But the same experiment being conducted in the US, if it gives you some other value, do you have a law then? You don't have a law anymore, right? So one type of input has to give the unique, like one output again and again. So that is, so predictability. You have to be like determinism and predictability. Without that, you do not have laws. In physics, there are no exceptions. If there is a law, every object is supposed to follow that law. Yeah. And only then we start calling it a law. If that has not been established, then law, we won't call it law. We'll start from principles, we'll start from, we'll call it theory, you know, theory of relativity, not calling it law of relativity, but Newton's laws. Yeah. So there's a way we move from small scale to, or uncertainty to certainty. And it's the predictability and determinism that helps us do that. We need that. Otherwise, there's no law. Also, causality, meaning the uniqueness of state. If a mathematical model yields two different values of position, like just like you were saying, one object cannot be at two different places in classical mechanics. In quantum, it can, okay? But in classical mechanics, it cannot be at two different places, fine. For a single fixed instant of time. So, what would this mean physically then? Is it possible physically? Like one object being at two places at the same time? Not possible, right? And that is why. So, this scenario is not possible in real world. And in physics, we deal with real world examples. Hence, that one-to-one mapping or many-to-one mapping is the only thing that makes sense in physics. Other mappings don't. Okay, follow? Right. Now we move to the next part. When does the class end? What time? 3:15. Okay. Uh, I mean, this will take up in the next class. Then we have 5-6 minutes. I mean, we have 2-3 minutes actually. So this is what we are going to do in physics. You're going to encounter linear, quadratic, hyperbolic, exponential, trigonometric functions. Okay, and a combination of all these. You might have a linear and a trigonometric function combination. You might have exponential trigonometric combination. You might have a combination of 3 or even 4 functions. Okay, so if you want to analyze these functions, if you want to play around, if you want to know the ins and outs of such variations, you should know how they look like. That's the first step. How does this graph look like on x and y plane? How does this look like on x and y plane? And so on. Okay. So in this class, I'll just show you where are you going to encounter what kind of function. You don't have to note it down. Just have to see what is in store for you. Since you've already studied 11th and 12th, you might have encountered those. You might be able to recognize those graphs as well. So let's get on. And yeah, we are going to talk about graphs of these important functions. See, linear graphs, where do we encounter? Different scenarios, right? In kinematics, we encounter it. In electricity, the relation, Ohm's law. In waves, frequency, h nu, or I mean, energy is equal to h nu, or frequency, okay, hc by lambda, or the frequency, I mean, speed of light, wavelength, and time taken. That relation is also linear, so that's what you see in thermal expansion. How the length of a rod changes when you increase the temperature, changes linearly. That's the formula. Hooke's law. In modern physics, also we have something intensity. Okay, photoelectric current, right? Okay, if you increase the intensity of the light, the amount of photons, the amount of electrons being ejected, that we call photoelectrons, increase linearly. More the intensity, the number increases. Okay, so I mean, in different chapters, you are encountering linear graphs. So wouldn't it be prudent? Wouldn't it be good to study linear graph holistically at the start itself? So whenever we encounter linear graphs, we know, okay, how to deal with this. What is it telling me? Yes or no? Okay. Then that thing, like projectile motion will be concerned with the entire thing. And yeah, hyperbolic, you can go through, I'll share these slides, and you might already know where have you encountered these graphs. The point here is just to show you that throughout the journey in physics, you'll be encountering all these graphs. And that's why it's important to study all these graphs one by one. And we'll do that in the next class. One final slide. Exponential graph, you can see where you encounter these. And it's not an exhaustive list. It's just to show you, okay, these are the places where we encounter such graphs. And from here, you can see the shape also, because we'll be looking at the shape of graphs, sinusoidal graphs or wave-like functions. Okay, we encounter all these. And here in our class, we'll see at least how to draw them. We'll start from this in the next class. Okay, thank you, everyone.